Bet. Good morning, everybody. Welcome back to Calc 1. Plan for today. We're going to finish off Standard 14, talking a bit more about linearizations and how to do tangent line approximations. Office hours are today at 11 and 1, tomorrow at 10 and 1, as per usual. As far as homework goes, don't forget we have an exam this Friday, Standards 1 through 14. And then we'll have this usual Standard 14 quiz on Monday before jumping into Standard 15 and start talking about optimization type problems, finding maxes and mins. Other than going to Dr. Schuller's house to look for dogs. A couple words about the exam. Unlike the first exam, this exam is not written with the idea in mind that you complete every question. I'm putting in there's a page of questions on there for every standard we've talked about so far, but for 65 minutes, what I would expect that you do is that you pick out 6 or 7 standards that you still need masteries in and try and focus on those. I've generally found that students, even if they still need say like 10 masteries or 12 masteries or something, tend to do better if they focus on only picking out 6 or so standards on an exam to kind of focus on and just spend their time on those questions, rather than trying to spread yourselves too thin and try to do every single standard. You can do that. If you have extra time at the end, you could try and do some more standards, but I would recommend focusing on 6 or so that you want to spend some good quality time on during Friday's exam. Yes?
Will the masteries be updated in Canvas before the exam?
Yes. Second order of business, Canvas. I have not yet updated Canvas with everyone's mastery totals. I was planning on waiting until the end of today because there's a few more retests coming in today, just so everybody's fully updated at the end of today. So later today, and I'll send an email out when I do this, I'm going to update Canvas with everybody's mastery totals, probably this afternoon sometime. Just like the first exam, you bring in one sheet of notes, front and back, whatever you want written on it. You can even use your sheet from the first exam if you like, and potentially add to it. As per usual, if you already have 2 masteries in something, you do not need to test over it. You can skip that question with a clear conscience. And if you can leave whenever you've done as many standards as you intend to. Either questions or comments related to this Friday's exam? All right, in that case, I've got a math problem for you. Did you know that $1 is equal to 100 cents? Probably knew. But did you also know that 100 is 10 squared, so we can write this as 10 cents, quantity squared. But what is 10 cents? Well, 10 cents is 1/10 of a dollar, so we can write this as $0.1 quantity squared. Because 10 cents and a dollar are the same. But what is 0.1 times 0.1? Well, if you square 0.1, you get 0.01. And $0.01 is the same as 1 cent, which means that $1 is equal to 1 cent, which means that $1 is equal to $0.01, which can be inferred from there that $1 is equal to $0, which means money is worthless and the economy is even in worse shape than you think it might be. Any questions or comments? I'm glad everybody's on the same page. All right, back to Standard 14 then. So the idea from Standard 14 was we were trying to see how can we approximate expressions like square root of 4.2. Okay, so what's actually wrong with this? I'll give you a hint. I'll give you a hint. There's some fishy business going on in here. Okay, then back to talking about tangent line approximations. So the idea that we were looking at back in Standard 14 is we were trying to find approximations for not so nice expressions like square root of 4.2. Where if we look graph out, we're trying to find the y value of this point right here, f of 4.2, if our function is f of x equals square root of x. But the problem was, how do we do that other than plugging it into a calculator? Okay, fine. But how does the calculator know how to approximate that? So the idea we had is, well, square root of 4.2 is not a nice number to find. So what we're going to do is we're going to pick a point close to 4.2, like at x equals 4, for instance. And what we're going to do is we're going to find a tangent line to the square root function at x equals 4, this nice point. That looks like a straight line. We're going to call this L of x equals the tangent line or linearization of f of x, taken at x equals 4 in this case, where 4 is a nearby point to 4.2, where 4 is something that's a lot nicer to try and take the square root of, because square root of 4.2, not a nice number. Square root of 4, that's just 2. So we take our tangent line approximation, and once we find a formula for this line, we can plug in 4.2 in for x into this formula. And we could say that the square root of 4.2, which we said last time was equal to f of 4.2, should be pretty close to L of 4.2. So, in other words, our idea of how do you approximate a value of a function at a not nice point like 4.2 is we pick a point nearby 4.2, like 4, that behaves a lot nicer. Take a tangent line to your function at that point, at x equals 4, say. Plug 4.2 into that formula for the tangent line, to the linearization, and use the fact then that your tangent line approximation, L of 4.2, should be, hopefully, pretty close to f of 4.2. And last time when we tried this out, we were able to get an approximation for square root of 4.2 that was close enough, according to Reagan, our engineering expert. And the formula that we kind of derived as part of the process for how do you find your tangent line, taken at the point, let's say x equals a, is the function L of x equals f of a plus f prime of a times x minus a, which we derived last time using the point slope formula of a line. Where in this case we had a equals 4 as sort of being the nice point that we could plug in for a in this formula. So any questions or comments before we look at some more examples? All right, I need to erase this. Last chance to point out anything you don't like about it. James?
Is it that you squared the cents also?
It's that I'm squaring the cents at also. If I take 10 cents and I square it, I'm not going to get 100 cents. What I'm going to get is 100 square cents. And similarly down here, when I take $0.1 and square that, what I'm going to get is something like 0.01 square dollars. What's a square dollar, you might ask? Take a dollar bill, cut it, into square. No, it's a new unit of measurement where you're somehow multiplying dollars by themselves or multiplying cents by themselves. Doesn't make any context, but if you're not careful about your units, the moral of the story is you can tank the entire economy. I think there was an episode of like Rick and Morty a couple years back for anyone who watches that show where like Rick hacks into the galactic government citadel, changes the value of the dollar to be worth what, so that $1 is worth 0 of itself, and the entire government collapses. Goodness gracious. All right, let's do another tangent line approximation. So, I'm going to be on the third page of the packet. Let's approximate 1 over 4.9. So here's the idea. We're going to look at the function f of x equals 1 over x. Let's say 5, spoiler alert, let's say 4.9 is about here. And we're looking at f of x equals 1 over x. And what I would like to do is I would like to approximate what should 1 over 4.9 be. I mean, that's something, again, we can plug into a calculator. If we did that, we'd get 1 over 4.9 is about 0.20408, blah, blah, blah. And the question is, I want to find a point that's close to 4.9 that we can use to approximate this value. Something that we can plug into 1 over x a lot easier than we could 4.9, but that's still pretty close to 4.9, so that if we take the tangent line at this nice close by point, we can use it to approximate what f of 4.9 is, or what 1 over 4.9 is. So what do y'all think? What would be a good point close to 4.9 that we could, that's a lot easier to plug into f of x than 4.9 itself would be? Morgan?
5.
Yeah, so 5 is pretty close to 4.9. Do you know what 1 divided by 5 is?
No.
You don't know what?
I mean, 0.2.
That sounds like two very different answers. I don't know what it is. Oh, it's 0.2. But yeah, I would agree. 5, I would say, is a very close by point to 4.9. I blurted it out earlier by accident. A lot closer, by the way, than what you would visually see looking at this graph right here. I'm exaggerating the distance between 4.9 and 5 so that the picture is easier to see. So the idea is going to be, let's find a tangent line to f of x at x equals 5. And while this top point here is going to be f of 4.9, this bottom point, L of 4.9, should give us an approximation for what f of 4.9 is. So, in other words, our nice point near we'll call it 4.9, is going to be a equals 5, according to Morgan. And I agree, I think that's a good choice of a point that's close to 4.9, that's relatively easy to plug into 1 over x. A lot easier than plugging in 4.9 at any rate. And so what I want to do is I want to find our tangent line approximation L of x at that point, and see what it gives us when we plug in 4.9 for x after finding this formula. So we're going to be working with a is equal to 5 here. 5 is our nice point. Morgan already told us what f of a should be. Well, that's f of 5, which is 1/5, or 0.2 if you prefer. Before we start plugging in values into our tangent line approximation, what other number are we going to need other than 5 and f of 5? What's kind of the last piece of the puzzle that we're going to need before we can use this tangent line formula? Jonah?
X? X.
We are going to need x. I'll tell you what x is.
There we go.
That's 4.9.
Okay.
But what else do we need other than kind of our x value in that formula?
You need f prime of a.
Yeah, we need f prime of a. So, in other words, we need to know what f prime of 5 is. So I got to do a little bit of calculus here, because we need to know what f prime of 5 is, so we know what the slope of this tangent line is going to be in order to be able to effectively use it. So let's do a little bit of side work here. Well, we know f of x is 1 over x, which is the same as x to the negative 1 power. What would f prime of x be if f of x is 1 over x? Nolan? So in other words, what would you get if we differentiated x to the negative 1?
Negative x to the negative 2.
Yeah, negative x to the negative 2, or equivalently, negative 1 divided by x to the positive 2 power. So with that in mind, what are we going to get if we plug in f prime of 5, Liam?
So negative 1 over 5 squared.
Yeah, we're going to get negative 1 over 5 squared, which is the same as negative 1 over 25. I had to do a little bit of calculus to get that number, but that's going to give us the slope of our tangent line. N equals negative 1 over 25. And I think that's going to be the last piece of the puzzle that we need in order to help us find our tangent line formula. Because now we can use the fact that L of x is f of a plus f prime of a times x minus a. Well, we can replace f of a, and f prime of a now with the values that we found. F of a was our f of 5, which came out to be 1/5. F prime of a came out to be negative 1 over 25. And then we multiply all of that by x minus a, which is just x minus 5. And if we simplify that a little bit, we'll get 1/5 minus 1/25 x plus 5/25, so plus 1/5, which will give us negative 1 over 25x plus 2/5 is going to be the formula for our tangent line L of x. So in other words, if you want to find the y-coordinate of any point of any x value on this line here, you would just plug x into the formula y equals negative 1/25 x plus 2/5 in order to get what the corresponding y value would be on this tangent line right here, taken at x equals 5. So with that in mind, what's the last thing that we need to do if we want to actually get our approximation of 1 over 4.9? So right now we have this nice L of x formula, but we were trying to approximate 1 over 4.9 to begin with. So what do we do with this L of x formula? Aiden?
Plug in 4.9 for x.
Yeah, we're trying to use this tangent line to approximate f of 4.9. Well, we said L of 4.9 should be pretty close to f of 4.9. So what that means, goodness, it's hot in here, is that if we want to find 1 over 4.9, which we said was equal to f of 4.9, well, that should be approximately equal to L of 4.9. Which means we need to take negative 1 over 25 times 4.9 plus 2/5, which my spidey sense is going to tell me is not fun to calculate.
Yeah. Gotta do 1 over 4.9.
What's that?
That'd
Aren't we clever? How about we plug it in here instead? Because I think this might be a little bit easier to work with. This formula, this version of line. These are the same. This is just a little bit more simplified than this one. But I actually think this form right here might be easier to plug 4.9 in for x. Because 4.9 minus 5, that's a lot easier to evaluate. So if we do that, we'll get 1/5 minus 1/25 times 4.9 minus 5, which is going to be the same as 1/5 plus 1/25 of 0.1, because this comes out to negative 0.1, and negative times negative is positive. Let's see, 1/5 is 0.2, according to what Morgan said earlier. 0.1 over 25, oh boy. I think that's going to be 1/25 is 0.04. So a tenth of that would be 0.004. And I'm getting 0.204 as my answer. For the approximation of what we would expect 1 over 4.9 to be about equal to. Who wants to be my engineer for a day? Nora, thank you for volunteering. So Nora, we said that earlier that when I tried plugging in 1 over 4.9 into a calculator, I got 0.20408 ... Do you think that this gave us a pretty good approximation of what 1 over 4.9 would be equal to? These numbers, as our expert engineer, do you think that and that are pretty close to each other? I'd say so. They're what, like 0.00008 apart from each other? That's pretty small, I would say. Oh, do you have a question? You did something. Okay. So, same process that we did in Monday's class. We wanted to find f of 4.9. We said f of 4.9 is scary. Let's find a point that's close to 4.9, like 5. Find a tangent line at that nice point that's close by. And then once we found our tangent line, our L of x, which we had several different ways of writing out, we could then plug in 4.9 for x into that approximation and said, well, L of 4.9 is 0.204, so f of 4.9 should probably be pretty close to that. Any questions or comments about what we did there? So tangent line approximations are pretty cool. If you go on to Calc 2, you learn how to do better and better approximations. For instance, instead of taking a tangent line, we could take a tangent parabola or a tangent cubic function, or a tangent degree 100 function. And in fact, there's an entire branch of mathematics called numerical analysis that's basically designed around how do we approximate these values, which finding exact values for are quite difficult. If you want to know more about numerical analysis, it's required for our applied math major. It's Dr. Webster's specialty, in fact. It's not my specialty. He knows more about it than I do, but fun fact. Okay, what if we wanted to find 1 over 5.2? You think that this tangent line would give us a pretty good approximate? If we were to plug in 5.2 for x into this tangent line, do you think it would give us a pretty good approximation? Anna? Why?
Because it's so close to the point.
Yeah, if we wanted to plug in something like 5.2, this is what L of 5.2 would be. This is what F of 5.2 would be. Still pretty close to each other. What if we wanted to take 1 over, what did I see in the packet? 9.1. Emery, what do you think?
It wouldn't give me a good approximation because they're too far apart.
Yeah, they're really far apart from each other. If we were to try and graph what's going on at, say, 9.1, we would say that f of 9.1 would probably be up here, whereas L of 9.1 would in fact be way down there. So the point of the story is, if you want to find a good approximation, you want to pick a nice value of x for your A that's pretty close to the bad one, as close as you can get while still being a nice value. So for 4.9, for instance, 5 was a point that's close by that's pretty nice to plug into 1 over x. But if we wanted to approximate something like 1 over 9.1, I would pick another value of x that's closer by to do our tangent line approximation. Say x equals 9, maybe. 1, 9's not so bad. That's 0.111111111 going on forever. Alrighty. I'm going to skip the next page in the packet. Alright, your all's turn. Let's say I want to approximate 1.01 raised to the 8th power. That one theoretically you could do by hand. Just multiply out 1.01 times 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 1.01. Not pretty, not fun. You could conceivably do it. How can we use a tangent line approximation or a linearization approximation, whatever you want to call it, to maybe try and approximate this value? So this time, if you notice, I'm not giving you an explicit function or an explicit nice value of A to work with. So if you give me something like this, the first thing I want to do, I would say, is I want to find a function f of x that if we were to plug in some number c into this function, it would give us 1.01 raised to the 8th power. So looking at 1.01 raised to the 8th power, what do you think your the function's going to be that will be that we would want to work with? An exponential, like what? It is. Can you give me what specific exponential function you want to work with here?
Oh, x8.
That's not an exponential function. I think power function is what you want to say.
Oh.
Yeah. Exponential would be like 8 to the x, where x is in your exponent. But yeah. So Emery has suggested Well, let's look at the function f of x equals x to the 8th power. That sounds reasonable. The expression we're trying to approximate is taking something to an 8th power. So what value would we need to be plugging into f of x equals x to the 8th that would be giving us 1.01 to the 8th? This one's not a trick question.
1.01.
Yeah, 1.01. So, in other words, if we plug 1.01, which I'm going to call c, into our function f of x equals x to the 8th power, that should give us what I would say is a pretty good approximation for what, or not approximation, that would give us exactly 1.01 to the 8th power. So it's totally possible that, say, on the exam or on a quiz, I could give you something like this, just say, approximate 1.01 to the 8th for you. And what you would have to do is you would have to sort of recognize what function do you want to be working with at what point. In this case, f of x equals x to the 8th at c equals 1.01. So, next step we want to do is we want to find a value, or find an x equals a that's near our value of c here. That's nice to plug into f of x. So in this case, we want to find a point A at which we could actually take our tangent line approximation. So what would be a value of A that we could use here, the point at which we're going to take our tangent line, that should be close to 1.01 and is something that we can take to the 8th power a heck of a lot easier than 1.01? Anna? A equals 1? James?
Yeah, I was gonna say 1.
I think that's a nice logical choice. Pretty close to 1.01, pretty easy to take to the 8th power. And then, without even drawing a picture necessarily, we can come up with our formula for what we would expect the tangent line to be. So, before we find our tangent line, we need these three pieces of information: A, f of A, and f prime of A. So we'll need those to take a tangent line, or the tangent line to f of x at x equals a. So we need to know what f of a is. Well, f of a, by definition, is just f of 1, which is 1 to the 8th power. Caleb, what's 1 to the 8th power going to give us?
1.
That one's pretty simple. We also need, because 1 to any power is going to give us 1, we're also going to need f prime of a. So let's do a little bit of work up here. If f of x is x to the 8th, what's f prime of x going to be, Anderson?
It's gonna be 8x to the 7.
Yeah, it's going to be 8x to the 7th. So with that in mind, if f prime of an arbitrary x is 8x to the 7th, Kate, what's f prime of 1 going to be in that case?
8.
It's going to be 8 times 1 to the 7th, which is 8 times 1, or 8. And with that, we have all the pieces of information that we need to use our linearization formula. This L of x equals f of a plus f prime of a times x minus a. Because if we write this out, we'll get f of a we said was 1. F prime of a we said is 8. X minus a is going to be x x minus 1. And if we write that out to simplify, we'll get 1 plus 8x minus 8. So we'll get our formula for our tangent line at x equals 1 would be L of x is 8x minus 7, I believe. Same process we did over here. Once we find our nice point that we're going to take our tangent line at, we just plug in all of the f of a, f prime of a, and a that we get from, well, plugging in our nice number 1 here into the original function, as well as the derivative of that function. We'll finish it off over here. So, once we find our tangent line at x equals 1, we got a tangent line of L of x equals 8x minus 7. What's our last step that we need to do in order to find our approximation for 1.01 raised to the 8th power? Marty?
Plug in 0.1.
Plug in 0.1?
1.0.
1.01. Plug it into what?
Our function. L of x.
As I say, don't want to plug it into f of x because that's the thing we were trying to avoid. But we could plug it into L of x a lot easier. Because by definition, 1.01 to the 8th is just f of 1.01. That's hard to find. But if we use our tangent line approximation, that should be close to L of 1.01. And if we plug in 1.01 for x into that formula we just found, we'll get 8 times 1.01 minus 7. Franklin, what is 8 times 1.01? Not 8.01. Careful. You need to multiply all of it by 8. Well, if we tried to do, I don't think so. If we were to multiply this out, we'll have 1 times 8 is 8. What would the hundreds place be if we were to multiply 1 by 8? Yeah, it's going to be 8.08. The 1 needs to be multiplied by 8, but the 0.01 also needs to be multiplied by 8. Minus 7. And in the end, we get an approximation of 1.08 as our approximation for what we would expect 1.01 raised to the 8th power to be equal to. Questions, comments, concerns? All right, Nora. So, you're our resident engineer. The actual value of 1.01 raised to the 8th power, we said, was 1.0828, actually it's equal to that, 1.0828 ... Would you say that's a pretty good approximation? I would agree, it's pretty good. It's not as good as the last approximation was in the previous example. This one is about 0.0028 off, as opposed to the 0.00008 off that the last one was. That's due to the fact that 1.01 grows really, really fast. In fact, if we were to try and graph out what we just did, it would be something like for f of x. And so this would be at 1, this would be at like 1.01, would be like way up here. And even at the top, so f of 1.01 would be here, and L of 1.01 would be here. So even at 1.01, which is really, really close to 1, the tangent line and the function have already started to diverge a fair bit from each other. Just because this function, f of x, grows really fast, x to the 8th power. It's like a parabola, but grows even faster. So this approximation ends up being pretty good, I would say. But not as good as our previous one was because our function didn't have as much diverge from the tangent line as much in our previous example. Even though 1.01 is really close to 1, relatively speaking. Questions or comments? Yeah, Franklin?
So why did we not plug in 1.01 back into the formula of A plus X prime of A times X plus A?
Back in here?
Yeah.
We actually did plug in 1.01 there. We just plugged it into the simplified form, 8x minus 7.
Oh, I see.
But 8x minus 7 is what we got from this formula to begin with. If we had wanted to, we could have plugged it in way back up there. We would have gotten something like L of 1.01 is equal to 1 plus 8 times 1.01 minus 1. Which actually would have been a little bit easier. We would have gotten 1 plus 8 times 0.1, which is 1 plus 0.8, 0.08. Wait. Plus 8. What am I doing wrong? I know 1 minus 1. Oh, I'm missing the 0. That's what I'm doing wrong. Which would have gotten us the same answer. So whether you plug it in like way up here at the top, or if you kind of simplify first and then plug in, say, 1.01, should give you the same answer either way. Because they're the same equation, just written in a slightly different form. I've got a question. Why didn't we just try and take a tangent line approximation at 1.01 to begin with? Like we picked a point A equals 1 that's close to 1.01, but we could have gotten even better by just taking A equals 1.01. Why didn't we do that? Jonah?
Because find out f of a, and if f of a is 1.01, then you're still doing 1.01 to the 8th, which you don't want to be doing.
Yeah, we're trying to approximate our value.
Yeah.
If we wanted to take a tangent line at 1.01, obviously that would give us a better approximation. But keep in mind, we have to find f of a and f prime of a. So if we were to have to find f of a when a is 1.01, well, that's the thing we were trying to avoid doing in the first place. So you always want to, so you don't want to pick your a, the point at which you're taking the tangent line, to be the point at which you're trying to approximate the function, in this case 1.01. You always want to pick a nicer point nearby. And I say nicer because for your a value, because you're going to have to find f of a and f prime of a. And you always want to pick a point where it's easy, or relatively easy to do that. These two values didn't take us too much effort to get, whereas plugging in f of 1.01 or f prime of 1.01 would have been a lot more hassle.
And also, if you plugged in 1.01, wouldn't it just leave you with a f of a at the end?
It would. It wouldn't be an approximation. It would give us the exact answer we're looking for.
So you'd spend all the time looking for the derivative just to not use it.
Pretty much, yeah. We would end up with something like, L of 1.01 is f of 1.01 plus f prime of 1.01 times 1.01 minus 1.01, which is, well, hey, that's 0, so this whole term goes away, so you're just left with finding f of 1.01, which gives you the exact answer, but also doesn't give you any sort of approximation per se. It's just literally you're plugging it into the function, which is exactly what we're trying to avoid. Are there questions or comments? In that case, if you flip the page to the next page of the packet, I give you two more expressions. 4 over 2.1 quantity cubed and sine of pi over 5. Both of which are not very nice numbers. What I'm going to challenge you all to do is to take a few minutes, talk with your neighbors, and see if you can use some tangent line approximations to approximate what these two values would be equal to. And just so you know, this is what the standard 14 question on the exam and on the quiz is going to be. I'm going to give you something that's not very nice, like sine of pi over 5, or 4 over 2.1 quantity cubed, and tell you, approximate this value for me using some linearization. So as a reminder, you're going to need to find what's your function, and what's the value you're plugging in C that would give you the nasty expression. Find the value of A that's near your value of C. In this case, you're probably going to want C equals 2.1. Find a value of A that's near that, that's a lot easier to plug in for f of x. Find the tangent line approximation at your x equals A being your nice point. And then finally, take L of whatever your C is, the not so nice number. Let's go ahead and take a few minutes, talk to your neighbors, and see what you can make of approximating these two expressions. Here's kind of the first few steps you might want to think about going through. What's your function? What's your C, that's your not nice value? What's a nicer value of A that's near that? The second one, by the way, I gave you a copy of the unit circle. Help you out. As always, share ideas with your neighbors and or flag me down if you're feeling stuck or not quite sure where to start. So I think you want your A to be 2. I don't think you want your C to be 2. C is going to be 2.1, the number you would actually plug in if you wanted to find this exactly. But yeah, your A could be 2, which would be 4 over 2 cubed is 4 eighths is 1/2. Yep. So, and then you would need your F prime of 2. Well, keep in mind, you're not taking F, you're taking F prime of A, not F prime of F of A. So your A is going to be just 2 in either case. So you would plug in negative 12 times 2 to the negative.
Oh,
Yeah.
which ends up being negative 12 times 1/2 positive power. Yes, and then those are the three numbers you'll need to find your L of x for.
Yeah.
Hi,
Hi.
what's up?
Oh, I just didn't know how far you want us to go down to simplify, just because it's like.
I don't think that one you can really simplify anymore,
Yeah, numbers.
or at least not get a nice decimal for it unless you were to plug that into your calculator, which
Yeah.
is what we're kind of trying to avoid. What's that mean?
Is this right?
I don't know, I didn't. Oh, tell me what you did. So you used a equals 2, I like that. So your f of a is a half, your f of a. So you wrote it as 4x to negative 3, so differentiated, that gives negative 12, x to negative 4. So that would give you negative 3/4. Looks like you set that up correctly. So one thing you might try and do, if you want to see did you do it right, is compare that to the actual value of 4/2.1. Do you have a calculator ready?
Yeah.
I was gonna say,
Okay.
try plugging that in.
Yeah.
Actually, that's a good question. So we get when we actually plug these in.
Did you plug it into? Yeah. I need to plug it in.
So the first one, if you plug in 4/2.1 cubed in exactly, you get about 0.4319. So hopefully your approximation for the first one ends up being somewhat close to that number. Hey, Emery. I don't know, what is that? Let's take a look.
Did you just do sin of x or sin of x?
Try plugging 2.1 up maybe in this step right here. That might be a little bit easier to kind of evaluate out than what you have. But it does look to me like you're on the right track. It'll be with you just a second. Well, that doesn't look like what you want. So you picked an 8 equals 2. I think that's a good point. That's close to 2.1 and a lot nicer to plug in. So I think your f of the, what I disagree with is your choice of f of x. I think your f of x needs to be 4/x cubed rather than just plain old x cubed. Because I think what you just found was an approximation to that rather than that. So keep working with that choice of a equals 2, but I would recommend using this function instead of what you have. What's up? Oh no! Oh, horrible. If you want, you could plug in 2.1 up here. Might be a little bit easier to evaluate.
Oh, yeah.
Let's take 0.01 times 3/4. Hint, 3/4 is 0.75, so 0.01 times that would be 0.0075, I think. Okay. All right. Finish book. Yeah. Numbers. For the second one, don't expect to get a particularly nice answer. Everything going all right back here?
Do not get a nice answer.
Good, then you're on the right track. Actually, here, let me grab my answers, I can compare, see if I agree. Oh, okay, just I actually applied it 6 months.
I was trying to do that, I was like, oh, no.
I think they're about the same level of niceness, which is not
I
particular.
just thought because,
Same X and Y coordinates.
yeah, that might make it simpler.
I think not particularly, because for my F of A, I did, yeah. F prime of A, my F prime of A was square root of 3 over 2. Yeah, no. Yeah, for something like sine of 5 over 5, I purposely gave you that because there's multiple values you could use to approximate.
You just leave it then, like, you simplify as far as you can, then leave it.
That's how I left it.
So I will.
What's up? Well, what's your A? Yeah, so you plug 2 in for x into your original function f of x, so you get 4 over 2 cubed, which is a half. Your f times. I'm actually be careful here. I don't think you differentiate it correctly. You get negative 12. What's negative 3 minus 1? So I think that's going to change what your f prime of A was. But otherwise, it looks like you set it up correctly. Oh, and also keep in mind when you plug in A at the end, your A was just 2 times half. If you remember. A lot of numbers floating around. Sometimes it's hard to make sure you're plugging them into all the correct places.
Yeah, dude, you can look at this.
Yeah, actually, I like that, but,
Oh,
And I think I don't like this.
but yeah, it's nice.
Oh, the negative 3. I don't like this.
No, very nice.
Since the derivative of 4 over x cubed is not negative 12 over x squared. What's negative 3 minus 1?
Oh,
Sometimes those derivatives can be sneaky. So let's come back together so we can at the very least talk about this first one for a second. This 4 over 2.1 cubed. So what I did for this one was I plugged in f of x equals 4 over x cubed at c equals 2.1. Because if you plug 2.1 into f of x here, you get 4 over 2.1 cubed. So what's a value of a that's near 2.1 that's a lot easier to plug into this function, would you say? Yeah? A equals 2 I think is nice. 4 over 2 cubed is a lot easier than 4 over 2.1 cubed. So we have a equals 2. Our f of a is going to be f of 2, which is 4 over 2 cubed, which is the same as 4 over 8, or a half. If our f of x is 4 over x cubed, which is the same as 4x to the negative 3, what would our f prime of x be? Alrighty.
Negative 12x to the negative 4.
Negative 12x to the
Negative 4.
negative 4? I like it. And negative 3 minus 1 is negative 4, not negative 2. Like something forgetting. which is negative 12 over x to the 4th power. So if we were to take f prime of a, we would get negative 12 over 2 to the 4th, which is negative 12 over 2, 4, 8, 16, which I think comes out to negative 3/4. And then, if we set up our tangent line formula, we get L of x is f of a plus f prime of a times x minus a, which is the same as 1/2 minus 3/4 times x minus 2. I'm actually not going to simplify this because I think we're going to be plugging in 2.1 in a second in for x, and I think plugging in 2.1 here is going to be easier than plugging 2.1 in if we simplify this. So then our f of 2.1 would be pretty close to L of 2.1, which is 1/2 minus 3/4 times 2.1 minus 2. Which I'm running out of space. I'll do it. Which is going to be the same as 1/2 minus 3/4 times 0.1. Well, that's 0.5 minus 0.75 times 0.1. Which is 0.5 minus 0.075, which is 0.45. Is what I got for my answer for that. Hey Nora, resident engineer. If the actual answer is about 0.4319 and we're getting an answer of 0.425, is that a good enough approximation? I'd say it depends on what you want to do with it. This one's getting a little bit far carried away. It's almost a whole 0.01 off, 100th off, which depending on what you want to do might be close enough or it might not be close enough. If you're wanting to build a bridge, I would be a little sus about that. All right, that's it for standard 14. I'll post solutions for standard 14. There's a few practice problems left in the packet that we didn't talk about in class. Encourage you to take a look at those. And with that, see you all on Friday for the exam. Have a good one. Take care.